Welcome everybody. In this video, I'm going to be solving free response practice 1, question 1, that qualitative quantitative question. First, this video is optional. You don't have to watch it. You could watch the whole thing. You could also skip ahead if one of the letters, one of the sections kind of threw you off a little bit. Why I might recommend you watch this whole video is that I'm going to approach these problems like I'm taking the AP exam. I'm going to read the question. I'm going to kind of speak out loud what I might be thinking in my head as if I was taking this test. I'll also maybe shout out a couple of recommendations as we go. I'll also have my phone so we can check the time, see how we're doing with that. And we'll see how my answers compare to the solution guide. Now, obviously, full disclosure, I've seen this question before. I've written out solutions to this question before. My answers might very well be different than when you're seeing a problem for the very first time. So I understand that. But I'm still going to try and take my time and think about it and process it again out loud in a way that I think would be beneficial to you. Okay, are you going to get all the points on the free response? No. And to be honest, it's quite likely that an AP physics teacher wouldn't get all the points either. I could guarantee I'd get a 5 on any AP exam, but I don't promise I'd get all the points on free response because sometimes they kind of nitpick or they want something specific. Remember though, our goal is to get half the points. So I think if you follow this strategy, like, oh, okay, I see how he did this and he made sure to do this, I think it'll help you get all those points. Okay, so we're going to go ahead and get started. I'm getting my timer ready. This is the qualitative quantitative test. That means we have 25 minutes. I'm going to start my timer on my phone. Here we go. Okay, the test is starting. Question 1, the qualitative quantitative test. It says the left end of a rod of length D and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot. Oh my gosh, as shown above. Okay, so it says a top view. So I'm looking down, kind of looks like our door problems we've seen where you're throwing something at a door. We have a pivot, so this rod here can rotate like this. We have this disc, kind of looks like a ball, but this disc is coming in, and we know that the length of the door or the rod is D, and where this disc is coming is a distance x. Okay. Point C marks the center midpoint of the rod. All right, that makes sense to me. The rod is initially motionless. But is free to rotate around the pivot, okay? The student will slide a disc of mass m disc, so this right here has a mass of m disc, toward the rod with a velocity v naught. They have the velocity right there. Perpendicular to the rod. Okay, perpendicular, no weird angles. And the disc will stick to the rod a distance x from the pivot. The student wants the rod disc system to end up with as much angular speed as possible. Okay, so they want the disc to stick. It is going to stick. We want the most speed as possible. The left end of the rod, a length D, and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot. Okay, I don't have to worry about any friction, as shown above. Point C marks the center. The rod is initially motionless, so this has an initial velocity here of 0 speed. Okay, it slides a disc of mass m disc toward the rod with a velocity v naught, perpendicular. It sticks to the rod. The student wants the rod to end up with as much speed as possible. Okay, I think I understand the scenario. Question 1. Suppose the rod is much more massive than the disc. Okay, so this rod has a lot of mass. It has a lot of inertia. Okay, to give the rod as much angular speed as possible, should the student make the disc hit the rod to the left of point C? Okay, point C. To the left of point C, at point C, or to the right of point C? Okay, I'm going to choose an answer and then, without manipulating equations, briefly explain our reasoning. Okay. So the question is asking essentially, where should I be launching this disk to give the rod as much speed as possible? So I want this to have a big angular speed. All right, should I fire this disk here, here, or here? Okay, well, let's see. When the disk is hitting, remember it's sticking. It says that in the problem. Seems like a collision problem. Well, with collision problems, I use momentum. It's also asking about like distances away, and I know like, torque has to do with distances away. I know that like obviously there's going to be a force from this disk. The disk is going to hit the rod, it's going to apply a force. The torque is going to be based on how far away from this pivot. I know that torque is equal to the force multiplied by x. Okay, so if the disk hits farther away, x will be larger. Okay, so farther from pivot, x will be greater. So torque is greater. More torque means more speed. Oh, God. I mean, that's not a very deep physics explanation, but I'm just trying to hit some main points. More torque means more speed. If I have time, I'll go in and maybe I'll talk about like acceleration or something. But okay, so I'd get more torque if it's farther to the right, and that would make it have more speed. That makes sense. Okay, I'm going to choose right here, to the right. I'll come back if I have time. Let's keep going. B, on the internet, a student finds the following equation for the post-collision speed omega of the rod in this situation. Omega, what's omega? The post-collision speed omega of the rod. Okay, so that's the speed of this rod after the collision. So omega is equal to the mass of the disk times x times v naught divided by I. Regardless of whether this equation for angular speed is correct, does it agree with your qualitative reasoning in part A? Let me read that again. Regardless of whether this equation for angular speed is correct, does it agree with your qualitative reasoning in part A? Okay, so does this equation match what I said here in part A? Okay. In other words, does this equation for omega have the expected dependence as reasoned in part A? God, this is kind of a weird question. But it seems to be asking, does this equation, whether it's right or wrong overall, does it match what I say here? So I should look back at what I say here and see if I can find data from this equation, details from the equation that say yes, it matches, or no, it matches. Okay, so let's see. My explanation here was all about I wanted to have more torque. I wanted to make torque big so I get a lot of speed. Does it talk about torque in this equation? mxv. There's no torque, at least obviously, in this equation. Oh man, this is a little tricky. Let's see. What else was I saying here? Besides saying torque, I said, oh, farther from the pivot, x will be greater. So if x is greater, the torque would be greater, and therefore the speed is greater. So I'm kind of using this idea, and again, that's kind of the basis of the question, right? How far away? So if x is larger, if it's farther away, the speed will be greater. Let's see, do I have like x? Oh, look right here. I have x right at this spot. And let's see, x is in the numerator, it's in the top, which means according to this equation, if x is bigger, the speed is bigger. And is that what I said here? Yeah, I said if you're farther to the right, you have more x, you have more speed. So, okay, I'm going to write something down. To be honest, if I have more time, maybe I'll look at v naught and I later on. Okay, but my explanation was kind of based on torque. Crap, I don't see torque anywhere, but based on x. So I said in A that if x bigger, speed is bigger. Speed bigger. Okay, I'm not using the word it or anything, am I? Maybe I'll put down omega so they know what I mean by speed. Okay, the equation does match because x is in the numerator. Oh my gosh. Maybe I could go back and say like more detail, like if I make x bigger, it's in the numerator, therefore what happens on the right side has to equal on the left side has to make it get bigger too. So I'll get to that later. But okay, so I'm going to say yes based on this x part right there. Okay, I'm going to keep going. Let me check how I'm doing on the clock. I have 8 minutes down, 8 minutes and 30 seconds. Let's keep on going. Okay, letter C. Another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with omega equals I x v naught divided by m disk d to the fourth. Okay, it says they make a mistake, so this equation isn't right. Without deriving the correct equation, I'm not doing any math, at least to derive the actual omega, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. Briefly explain your reasoning. Another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with this equation. Okay, so I'm going to look at this equation. This equation is wrong. How can I tell this equation is not plausible, is wrong? How do I know it doesn't make physical sense? Okay, so again, let's look at this equation and see if it matches or what doesn't make sense. So omega is equal to I. What was I? If I go back up here, left, rotational inertia I. Oh, I is the rotational inertia of the rod. Okay, the rotational inertia of the rod. Oops, I'm right here. So I is the rotational inertia of the rod. It's in the numerator. So that's saying if the rotational inertia of the rod is big, the speed would be big. And this is, again, the speed of the rod. Does that make sense? If the rod has more and more inertia, would, after the collision, it have more and more speed? Well, I don't know if that makes sense. Because like the disk is applying a force, it's going to apply a torque, and I know that torque is equal to I times alpha. And you know, like during this hit, during this collision, whatever the torque is, again, if we just assume it's at some spot for this point here, the torque will be some number. If I have some value of torque and I have more and more rotational inertia, well, I should have less and less acceleration. Let me get my eraser out. This doesn't seem to make sense, right? And this should make sense also. Like, if I have something that's really massive, it's probably not going to move as fast after a collision. Yeah, if this was like a toothpick and I flicked a ping pong ball at it, the toothpick would rotate. But if this was, say, I don't know, like a 2x4, right? A big wooden beam, and I flicked a ping pong ball, it's not going to move that much. I don't think this equation is right because inertia shouldn't be on the numerator, on the top. So rotational inertia of rod shouldn't be on top. By second law, more inertia means rod's acceleration is less. I should try and connect that to omega, right? Because they are talking about omega. So omega less. Again, boy, Mr. Thrasher would really be yelling at me because I'm not like showing an equation linking these things. Maybe I'll go back if there's more time. To be honest, I kind of stopped after this one. Should I keep going? I mean, maybe some of these other ones come into play, but it doesn't say like list all of them. Just how do I know it doesn't make physical sense? I'm pretty sure I doesn't make physical sense based on Newton's second law. If I have time, I'll come back. Okay, but let's see. Let's go on to D. For parts D and E, do not assume that the rod is much more massive than the disk. Okay, so don't assume this is way more massive. So I can't make like a sentence saying like, well, let's pretend the rod is the mass of a train and the disk is a ping pong ball. And because this is so much more massive, this angular speed or something would be 0 anyway. I think that's what they're meaning, and that is what they're meaning. Okay, well, so I can't just assume one of these things is going to stay stationary. Okay, they could potentially both move, they could potentially both have the same approximate masses, so there could be rotations and things. Immediately before colliding with the rod, the disk's rotational inertia about the pivot is mx squared. So this is the disk, that's this thing. This is the disk's rotational inertia of the disk. And its angular momentum is this. Okay, so angular momentum, remember that's L. So L disk. Angular momentum with respect to the pivot is m disk v naught x. Derive an equation for the post-collision angular speed omega. So we still want this omega. So now derive, meaning come up with, use math, come up with an equation for the post-collision angular momentum of the rod. Express your answers. Okay, so no numbers, we're just doing algebra and physical constants. So let's see, again, it's a collision. They're giving me angular momentum. Seems like this is going to be a conservation of angular momentum problem. So, all right, what do? I say the initial angular momentum is equal to the final angular momentum. If I remember in the beginning, it says that the rod is initially motionless. So it doesn't have any speed. So in the beginning, L naught, the only thing that has angular momentum is the disk. And then after, do they bounce or do they stick together? Let's see. It's free to pivot. They move towards each other. It's attached, motionless. The student wants the rods as much as possible. Oh man, where does it say whether they stick or not? Do they say it there? Do they say it back over here? Make a miss. Oops, not that one. When the rod, oops, not that one. I'm going to the wrong section. About the rod and his angular momentum. Where does it say? I thought it said it was sticking somewhere. Where did they say it was sticking? Oh, right here. The disk will stick to the rod a distance x from the pivot. Okay, so back over here. It's sticking. So we learned that when things are sticking, right, it's like one object. So this is going to be the angular momentum of the disk and the rod. Okay. Let's see again. The rod didn't have momentum in the beginning, so it's just the disk. What's the angular momentum of the disk? They gave it to us. It's right here. M disk, I'm going to put md v naught times x. There's nothing else for the rod because it's staying at rest. Now I got to combine these two things. And remember, I kind of combine their inertias and I multiply that by the final angular velocity. So I need the angular velocity of the rotational inertia. I add the rotational inertias of the two things and I multiply that by omega. Because remember, L is equal to I omega just in general. Yeah, okay. Yeah, that's right. Okay. So I need the rotational inertia of the disk. Am I given that? Ooh, right here. The rotational inertia about the pivot for the disk is m disk times x squared. Okay. And the rotational inertia of the rod was just I, plus I, just like that. Okay. So then what would I do? Just to solve for omega, I would divide. So I have I'll put m disk times v naught times x divided by m disk times x squared plus I, just like this. Oh gosh, maybe I could reduce, but this would be difficult to reduce. This isn't a super easy like fraction thing. So I'm going to leave it like this. Okay, and I think that looks good. Let me check my clock. How am I doing? I got 17 minutes and 30 seconds. So I still have about 8 minutes or so for my my time. So let's see. That's going to keep on going. Letter E. Consider the collision for which your equation in part D was derived. Okay, so I have this equation. I got some speed of the disk. Again, this is when they stick together and start rotating. when they stick together and start rotating. Except now, suppose the disc bounces. Suppose it bounces backward off the rod instead of sticking. So before, this whole thing was rotating like this and the disc was attached. But now we're looking at the scenario where now this is rotating and the disc is bouncing backwards. That's what they say. Is the post-collision angular speed of the rod, so this right here, when the disc bounces off, is it greater, less than, or equal to the post-collision angular speed when it's stuck? Okay, so we're kind of comparing sticking versus bouncing. When the disc bounces off, is this angular momentum going to be the same, more, or less than before? Okay. I feel like Thrasher told us about bouncing. How am I going to do this? Well, in the beginning, like the disc has a velocity like this, and then it sticks, and then right after the collision, it still has some velocity. Maybe it's a little slower. That probably makes sense. But now the disc, it started off going this way, some velocity up, and now it has a velocity going down. After, when it bounces, when bouncing, there's a larger change in velocity, right? If I'm moving like this and then I go slower, the velocity decreased a little bit. It changed a little bit. But if I'm going upwards and then I stop and then I go the other direction, that's a larger change in velocity. Remember, I have to think of my pluses and minuses, positive velocity, negative velocity. When bouncing, there's a larger change in velocity. When bouncing, delta V is greater for the disc. Okay, let's see. If the change in velocity is greater, well, the momentum must be greater. The change in momentum is greater. So, disc's change in momentum must be greater after bounce. Okay, now if momentum's conserved, and the disc has a greater change in momentum, the rod has to have a greater change in momentum. Okay, I got to go on to the next slide. Okay, if momentum's conserved, momentum is conserved, the rod must also have a greater change in momentum if disc is bouncing. Okay, and then, I know L is equal to I omega. So if the rod's change in momentum is larger, it still has that same rotational inertia. Omega must be greater. Okay, so omega must be greater if disc bounces. Okay, those big ideas. All right, and then let me go make sure I go back and say, okay, I said it was greater. Okay, let's see. That's all the questions. Let's see, how am I doing on time? I have 22:13. Admittedly, not a lot of time. Okay, I was adding some details in here, but I have about 3 minutes. Maybe I would go back and check over my work. Maybe I would quickly add a couple explanations to some of these things, but I'm pretty confident that I'm getting at least half the points. And again, if you're getting half the points, that makes you on track to pass the AP exam. You could test this versus the solutions that I've posted as well. Okay? But hopefully you saw that, I was hitting some kind of broad ideas. I wasn't giving super explicit, therefore this is true, therefore this is true, therefore this is true. Some questions you might have a little more time to go back and do that. Maybe for some of these, if I was getting afraid of the clock, like this one here, maybe I would have skipped a couple of these sentences. Maybe I just would have said momentum's conserved, bigger change in momentum when bouncing for disk, therefore bigger change in momentum for L, so speed is greater, something like that. But yeah, that's my approach. Notice that I did have time. I didn't assume I knew the question. I read the question. I even reread a lot of these questions. So you have time to do that. Okay, so again, I finished all of that, which probably had a little more detail than even I would recommend in some of my prior videos. I finished that still with 3 minutes to spare. Hopefully this was helpful. If you have questions about what I wrote out, by all means, feel free to send me an email or see me during office hours. Okay, thanks for watching this video.